Assalamualaikum and a very good morning to everyone. I'm Rosita Dola. Would like to welcome all of you to this 27 distinguished lecture series brought to you by Faculty of Engineering, and very special this time where we co-organize with Razak Faculty of Technology and Informatics, RFTI, the faculty where I am in now in University Technology Malaysia. Certainly, it's a great honor for me to host our honorable guest speaker today, the distinguished Professor Dr. Rohit Karnik from MIT Department of Mechanical Engineering, Massachusetts Institute of Technology in Cambridge, United States of America. Prof. Rohit Karnik was also my supervisor when I was a postdoc at his laboratory called Microfluidics and Nanofluidics Research Laboratory in 2 years' time from 2017 to 2019. And how time flies, Prof. It's already 1 year since I left MIT, my alma mater, and definitely I miss Boston so much. So today, the title of today's lecture is Unconventional Materials and Paradigms for Water Purification and Quality Control in the 21st Century. Well, I'm sure there will be a lot of interesting discoveries by genius Prof. Rohit Karnik as usual. So get ready, everyone. I still remember the time when I did my regular presentation in the lab group members. Your idea, Prof, was just amazing in making the research more impactful to the society. Alrighty, without further delay, I can't wait to have Prof. Rohit Karnik with us. Thus, I would like to proceed this session with our Dean of Razak Faculty of Technology and Informatics, Associate Professor Dr. Astuti Amrin, to give an introduction and biodata of Prof. Rohit Karnik. Over to you, Dean.
Thank you very much, Dr. Rosita Dola. Assalamualaikum, hello, and good day to everyone. Welcome to this 27 virtual UTM lecture series organized by Faculty of Engineering, UTM Johor Bahru. My name is Astuti Amrin, the Dean of Faculty of Razak Faculty, UTM Kuala Lumpur. It's my great pleasure to welcome Prof. Rohit Karnik from Massachusetts Institute of Technology, Boston, United States. A brief introduction about Prof. Rohit. Rohit Karnik is Professor and Associate Department Head of Education in Mechanical Engineering at the MIT, where he leads the Microfluidics and Nanofluidics Research Group. His research focuses on the physics of micro and nanofluid fluids and the design of micro and nanofluidic systems for application in water, healthcare, energy, and environment. He obtained his Bachelor Technology degree from the Indian Institute of Technology at Bombay in 2002 and his PhD from the University of California at Berkeley in 2006 under the guidance of Professor Arun Majumdar. After postdoctoral work with Prof. Robert Langer at MIT, he joined the Department of Mechanical Engineering at MIT in 2007. Among other honors, he is a recipient of the Institute Silver Medal, IIT Bombay in 2002, NSF Career Award in 2010, Keenan Award for Innovation in Undergraduate Education 2011, DOE Early Career Award in 2012, IIT Bombay Young Alumnus Achiever Award in 2014, and the Ruth and Joel Spira Award for Distinguished Teaching quite recently in 2018. Without further ado, the floor is yours, Prof. Rohit. Over to you.
Thank you very much. So good morning, everyone. It's a pleasure to be here. And thank you to the organizers for allowing me to share some of our work. So today I'm going to talk about our work on materials and paradigms for water purification and quality control. So just as a brief overview, we know that the amount of water on this planet Earth is quite limited. And in this picture, what you see, if all the water on the Earth were a drop, it would be about that big. And out of that, the liquid fresh water is quite a bit smaller. It's a small fraction of the total H2O on the planet. And the fresh water available to us is very tiny indeed. And so this creates the challenge of limited amount of water and water stress. So if we look at the United States, the western half of the country has very low rain, but that's also where quite a bit of agricultural production is. And as a result, we can see that there's a lot of withdrawal of groundwater. And so this leads to water stress. And this issue is widespread across the globe, where we see that many countries around the world have different degrees of water stress. So what are some of the challenges? And where does the water go? So agriculture turns out to be the largest consumer of fresh water. And so there's this interplay where if we don't have fresh water, it starts impacting agriculture and food availability. It can also impact energy. A large fraction of people, about 1 billion, lack access to clean water. And with the UN World Development Report, Water Development Report in 2009, there were more than 1 million children who were dying of preventable diarrhea due to contaminated water. And fortunately, that number is decreasing, but it's still too high. Arsenic pollution is a huge issue with about 140 million people affected in over 70 countries. Groundwater provides a large fraction of our fresh water, but it is being depleted. And so that is an issue. Also, we have ecosystem and other problems. For example, runoff from agriculture that's overloaded with fertilizers can cause algal blooms and other challenges. And so in this context, water quantity or availability is an issue, but there's all of these other challenges. And so quantity is not enough, but quality is also required. And water can have a lot of different contaminants. So if we look at this length scale going from nanometer scale to millimeter scale, there's a lot of different contaminants that can be there. So the water can be very salty. It could contain small molecules such as pharmaceuticals or pesticides or perfluoroalkyl substances. It could have viruses, bacteria, protozoa. It could also have microplastics, dust, and other particulates. So if we are able to purify water, we can actually reuse water or make more water available that was unsuitable for use. So in this context, I'm going to talk about 3 different directions that we have been pursuing. I'll spend more time talking about the first one. And this is at the nanoscale, so at the smallest length scales. We are trying to make membranes that are only 1 atom thick, which can remove salts and small molecules. Then going at slightly bigger scale, at the microscale, I'll talk about using naturally occurring membranes in this tissue called xylem as a filter for water. And then I'll end with a quick overview of our work at the systems level, which is advancing a new concept to measure trace contaminants in water. So to begin with the first, I'd like to point out that membranes have many advantages and they enable energy efficient separations. And this is an excerpt from an article a few years ago in Nature, which shows that of the total energy consumption, a large fraction is from industrial use. And out of that, by replacing thermal separations by membrane-based processes, maybe 90% of the energy could be saved. And this has already happened in the case of water. So if we have salty water, let's say seawater, we can pass it through membranes and using a process called reverse osmosis. So we have high pressure that squeezes the fresh water through and salts are rejected. And this process is more efficient. So you can see some of the membrane modules here. And the capacity around the world in terms of the desalination, you can see that the reverse osmosis membrane-based process that shot up, but thermal processes have flattened out. And so this is an example where membranes bring in advantages and reduce energy consumption. They're also more modular and therefore they are taking over some of the more conventional separation processes. So there's challenges with reverse osmosis, even though it's been an absolute game changer. So for example, the area of the membrane required can be really large. In some of the larger plants, it can even approach around 1 kilometer square of area. There is still a lot of room to improve the overall energy efficiency and amount of water that's recovered. And membranes are prone to fouling and scaling. So you can see in this photo here, salts can deposit, we can have microbial growth, and that affects membrane performance. And because the membranes have low chemical resistance, it's hard to control these fouling and degradation, and it leads to additional costs. In today's world, there's the additional issue of these small molecules that are emerging contaminants, which were not so common in the past, and we didn't know as much about them in the past. And many of these, we still don't know the effect of them being in water. And the conventional membranes that are used often do not effectively filter out all of these molecules. And so that's another challenge that we have to address. Also, if we want to operate at high pressure to squeeze out more water or have concentrated salt solutions, that can be a challenge. So to address this, people have explored various materials, and controlling the structure and chemistry of materials at the nanoscale has been an absolute key. So on the left here, there's this cross-section image of a polymeric membrane with a very thin selective layer. And the development of membranes like this was critical in making reverse osmosis a success today. And now people are looking at various other materials that are being explored for different properties, such as carbon nanotubes or zeolites or graphene-based materials. So several years ago, we started looking into this problem, and graphene really attracted us. So if we think about graphene, it's a single sheet of carbon atoms, and you can poke holes in it, which can be selective. So what are some of the advantages of a membrane like this? It's extremely thin. In fact, you can't make a membrane thinner than 1 atom. And so it has very low friction, and it could enable compact, energy-efficient separations. It's very strong, even though it's thin. And so it offers the possibility of going to high concentration or high pressure separations. We can make rigid and defined pores in the membrane, and so we can assure rejection of molecules beyond a certain size, at least in theory and hopefully in practice. It's very chemical resistant compared to today's membranes, so maybe there's opportunity for better cleaning and fouling control, and then use with more aggressive solutions, which normal membranes cannot handle. It's also designable in the sense that we can image and measure the flow through these pore structures and use that knowledge to design membranes. And finally, it's also scalable. And I'll show later that we can do roll-to-roll manufacture. But it is a technology that's very early stage. And when we started off, there was no nanoporous graphene membranes existing. And so we asked the question, how can we realize the potential of this material? And to do that, we need to control the pores in graphene. We need to understand how these pores work and how water or salts flow through them. And then also think about making practical membranes. And so we have been working on this for several years, and I'm going to share some of the results that we have. So how do we make these membranes? So graphene itself can be grown on copper sheets. And people have developed processes to handle it. For example, these roll-to-roll transfer processes. And my colleague at MIT, John Hart, and others have developed roll-to-roll synthesis processes that can make graphene at scale. So this process is called chemical vapor deposition. And at scale, it has potential to cost less than $10 per meter square. So we take this and put it on some support. For example, there's this polycarbonate trackaged membrane support that we have commonly used in the past. And so we can have a layer of graphene that can then allow selective support, selective transport. and it's placed on this support. So we can do this transfer very easily, take graphene on copper, press it on the support, etch out the copper, and we get the membrane. And you can see this little square here. It's 1 centimeter, roughly 5.5 to 1 centimeter area of 1 atom thick material that's deposited on the support. And we can see this electron microscope images showing graphene covering the pores of the support. So we can create holes in graphene, and we develop this process where what we can do is we can irradiate the graphene with ions, and these ions basically create these defect patches, and we can etch them out to create pores. So we developed this process based on some simulation work and experimental work on carbon nanotubes. And what we found is that we can indeed create pores which are sub-nanometer in size. So here you can see as the etch time goes from 0 minute to 2 hours, we get a nice pore size distribution where most of the pores are below 1 nanometer, and we can have fairly high density of pores of about 1 trillion pores per centimeter square. So is this membrane selective? And here is an image where we can see these pores in the membrane, and these are atoms of carbon. So can we make this selective? And so we did experiments where the membrane is mounted between 2 cells. We can put different solutions and measure diffusion. We can put different salt concentrations and measure the membrane potential and deduce the ion selectivity from that. And we can etch the membrane and then remeasure it to see how the etching affects the transport. So in this figure, on the x-axis, we have the etching time, which should grow pores in the membrane. And then here we are looking at the flux of 2 different species. So one is potassium chloride, salt, and the other one is this small molecule, which is about 1 nanometer or so in size. And what we see is as the etching progresses, the salt can go through first, but the large molecule, its flux or flow doesn't change till we get to a longer etching time. And so there is this window of etching time where the salt transport has gone up, but the molecule transport has not changed that much. And so this shows that we can create selective pores in the membrane that can regulate differentially the transport of salt versus a small molecule. And from the membrane potentials, we also see that there's some difference between the transport of potassium and chloride, and there's a mild selectivity for potassium, maybe because of the negative charges on the membrane. And so the picture that emerges is that as the etch progresses, potassium ions preferentially go first, then both potassium and chloride ions start to go, and as we etch further, everything starts to go. And this flux then flattens out because it's now governed by the support on which the graphene sits. So this was a first study that showed that we can actually tune the selectivity of a single atom thick membrane over centimeter square areas and start to see selective transport. And so it was very promising that we can develop this further for useful separations. So I talked about how if you make the membrane thin, it can offer very little resistance to flow, but it's also a challenge because now if you have a thin membrane and if you have a tear or a defect, then it's a leakage. And so we have spent a lot of time and energy in trying to really understand the origins of these leakage and figure out ways in which we can make the membrane robust against leakage. So there is 2 scales at which these defects happen. One scale is really at the nanometer scale where defects can happen in the graphene in the synthesis process or at wrinkles. And then there's larger defects which can be tears at the micron or larger scales. And so one strategy that we have developed is to really understand the interplay between the support and the membrane. And through doing simulations, we can come up with regimes where we can make the membrane defect tolerant. So let's consider this diagram here. If this black circle represents a support pore, This green area is graphene, which has a lot of small pores that are not shown. And let's say these red dots are defects in graphene, which will let everything through. So if we look at the transport pathways, we have the graphene pores, the leakage through these defects, and the support forming a transport network like this. And if the leakage resistance is low, then everything goes through the leakage. Graphene doesn't matter. So we cannot get selectivity. But now, if we have much smaller pores, which are smaller than the distance between these defects, then the picture changes. Now we have pores and graphene in series with the support, and the leakage pores also in series with the support. And if we tune the support resistance large enough, then the leakage will be low. And by doing so, we can actually reduce the leakage and make the membrane more defect tolerant. We can go one step further, and given that graphene actually does not allow things to go through unless there are holes in it, we can use this to localize reactions. So this is a very simple reaction that we did. It's a well-known reaction of polymerization to form nylon. So if we just take the support and introduce molecules on opposite sides, they are going to meet in the pores, and this forms a polymer plug that you can see labeled in red here. And this is a fluorescence microscope image. Now, if you cover it with graphene, wherever the graphene is intact, these molecules cannot pass through it, and therefore they don't form these polymer plugs. But if there is a tear, that's where plugs form, and they seal those defects. We can also do another thing, which is atomic layer deposition, which goes on to defects because that's a high energy of adsorption for the precursors used in the atomic layer deposition. So through strategies like this, we can reduce the leakage through the membrane. So with this reduced leakage, we were able to measure water flow. So in a similar experiment, we can put a draw solution, which will create an osmotic pressure difference, and water will go through, and we can measure the volume change. And we indeed saw that we are able to get the water to go through and reduce the rough permeance or the resistance to water flow of pores in graphene, which turned out to be consistent with the MD simulations from the Aluru group. And we can also now add different molecules or salts and see how they go through the membrane or not, and measure the rejection. So with this membrane, we are actually able to get rejection of small molecules and some rejection of multivalent salt, but not common salt. And the reason for that was there were still some non-selective pores, which were a little bit larger than the pores that we intended. So what we can do is basically use the fact that the membrane is so thin that molecules will be able to interact across pores in the membrane when the pores are large, but when the pores are small, they will not be able to interact. So it should be possible to selectively block these larger pores, and this approach is only possible if the membrane is so thin. And so using that, we are able to increase the rejection, and we are able to get rejection of common salt through these membranes as well. And just earlier this month, one of the former postdocs in our group, who is now a faculty member, he showed that we can get more than 99% rejection with nanoporous graphene membranes using approaches similar to what I just talked about. So we can get rejection of different molecules. And how about pressure? So it turns out that if you want to squeeze out as much water, and especially if you have salty brine, that often needs to be evaporated so that you can get a concentrated waste rather than a lot of brine that has environmental considerations while disposing. And so in treating that, it turns out that if we use thermal energy, the energy consumption is very high. But if we use reverse osmosis, then there's potential to significantly reduce the energy consumption. But today's technology cannot go to such high pressures. So we tested whether graphene is able to, or has the potential at least, to be able to operate at high pressures. And we applied high pressure and then measured the fraction of the membrane that failed by measuring the gas flow rate through it And then we also characterize the membranes. And what we found here in this AFM image is that even after applying 100 bar pressure, most of the graphene area is okay, except where we have these wrinkles. So this study and others that we have done showed that wrinkles are a weak spot, which we'll have to deal with, maybe by sealing these wrinkles or some other approach. But if we can do that, then the rest of the graphene is actually very robust mechanically, and it can withstand very high pressures. And this, the fraction of membranes that fail is a strong function of the support pore. So the stress in the graphene scales with the diameter roughly of the support pore. So if the diameter is high, then everything fails very quickly. But if we go to sub-micron diameter, most of the graphene is able to withstand high pressures. And if we go to few tens of nanometers diameter, then we should be able to create membranes that can withstand extremely high pressures. And so this is very promising in terms of being able to operate with highly concentrated solutions and high osmotic pressures, both for water as well as for chemical separations. So can we fabricate these membranes at scale? And this is one example where this is in collaboration with John Hart and Jing Kong. So we can basically fabricate these graphene in a roll-to-roll furnace on copper. This is in John Hart's lab, and you can see the photo here. Then we take this graphene on copper, we cast polymer, we do leakage sealing and do plasma treatment to create the membranes where you can see them here. So this is an SEM image showing graphene on a support. And so this is a fully scalable process. And here we applied it to dialysis, which is used for, of course, for patients who have kidney problems, and also in biomedical research and bioprocessing. And we can see that the membranes actually outperform commercial membranes in dialysis as well. So this illustrates that we can actually start to engineer processes that can make this scalable and cost-effective. So this is the first part of the talk, which I'm just going to briefly conclude. So we can show that we can take single-layer graphene, which is just 1 atom thick, and we can tune selectivity at the sub-nanometer scale by this nucleation and growth of pores using the ion irradiation method. We have defects in the membranes that can induce leaks, and dealing with defects is actually very critical to realizing functional membranes. And we showed that filtration at the molecular scale is possible with these macroscale single-layer graphene membranes. And they have several advantages, including high mechanical and chemical stability, assured size-based rejection, which will be very helpful for emerging contaminants, and ability for rational design, which will allow us to tailor these membranes to different applications. So the field of nanoporous graphene membranes is growing, with many more researchers now joining, and I haven't had the chance to talk about many of the great work that has come out from different groups. But we can say that the stage of infancy has passed, but it's not yet mature. So there is much more to be done, including fundamental understanding of flow at the nanoscale. We have some understanding, but we still don't understand many things. How do we create more precise pores in the membrane? How do we fabricate membranes, including quality control and leakage mitigation, and apply it to various applications? So I'll switch gears and talk about going one step higher in scale from the nanoscale to the microscale. And this is in the context of unsafe drinking water, which has microbial contaminants. And this affects a large number of people in the world. And approximately 1 out of 5 deaths under the age of 5 is due to waterborne disease. And the burden is borne primarily by people who are in developing countries and don't have access to resources. And household water filtration or water treatment can reduce the burden of waterborne disease, but there is challenges of awareness, affordability of solutions, access, and acceptance. So for example, if we look at different kinds of water filter, and this is from a survey that was done by an MIT group a few years ago, we have reverse osmosis, which is often used in urban India, for example, gravity-driven filters and conventional filters, where these are very effective, but they're unaffordable or out of reach. And the simple filters like cloth don't work very well against pathogens. So this is a survey by Grasp Analytic, which shows that people think that the cost of a water purifier is one of the biggest issues. And of course, it goes hand in hand with awareness, because if you believe that there's an issue with water that can have an impact on the health, then maybe the thinking will be different. But still, the perception is that water purifiers are too expensive. And so there is so low-cost water treatments at the household level are sought. So, for example, chlorination or ceramic pot filters are inexpensive methods, and each of the methods has its pros and cons. And so, definitely, the more the methods we can develop that have different attributes and different advantages, then we can hope to reach more people and provide more clean water. So the research that I'm going to describe, actually, the idea arose at this interesting conference. This was in Israel, where NATO brought together different groups. So one was engineers like me who are looking at fluid flow at the small length scale. And another was plant biologists who are looking at water flow through plants. And so that's where we had a lot of good discussions and about water flow in plants. And as you know, water goes through the roots and it goes up the plant and it evaporates from the leaves. And the tissue through which it passes is called xylem. Now, at the roots, water is close to atmospheric pressure. And then at the leaves, it evaporates under capillary action. And if we calculate the pressure drop along the length of a tree or the height of a tree, it turns out that water is actually under tension. So if you look at a plant around you, if it's sufficiently tall, it contains water which is at negative pressure, but it's still in liquid form. So it's metastable, and that's truly remarkable that, that plants actually rely on water being stable at negative pressures. So what happens, how do plants do this? If you had a small bubble that forms, then it will rapidly grow because the water is under tension. And so plants have developed this remarkable structure of the xylem tissue. So if you take this little pine branch and look at it under a microscope, this is what you'll see. There are these little channels going through. If we zoom in further, we can start to see some interesting features there. If you zoom in further, there are even more interesting features, little domes with holes, and then some spider-like structures. So these structures are actually critical in enabling water to exist at negative pressure in plants without drying up in the plant. So how does it work? So plants have these xylem tissues, and these little structures have membranes in them which trap air. So if you have a vapor bubble that forms, it cannot go beyond a certain compartment. And so this structure is compartmentalized, where water has to pass across the compartment through these membranes, and these membranes can effectively block vapor from going through. And if you look at the size of the pores in these membranes, that's small enough to actually filter out bacteria, protozoa, and some viruses. So can we use this naturally occurring membrane to make water filters? And if we can do that, then they would be very simple to make because the membranes already exist. We don't need to make membranes with features at the micro or nanoscale. If we employ sustainable practices, they can be eco-friendly. And in fact, the wood that has this xylem tissue is not very good for furniture and other applications. So it's more of a byproduct. And it can be very cost effective. So the wood that makes one filter about this big is less than 1 cent. And even with processing and other costs, the filters would be at most 5 to 10 cents. So what we did was to take this pine branch and see if it filters water. And indeed, we could see that it can filter out this dye. And if we look at bacteria, so this is fluorescently labeled bacteria, E. coli, and we filtered it and then cut open the filter, and we can see that the bacteria are actually lining up in these little chambers where we have the membranes. And SEM images also show that the bacteria are trapped in these membranes. And we were able to get more than 99.99% rejection of E. coli. So this was very promising. But we were a far way from practical use of xylem filters. So one was there was no prior studies of xylem as a material for water filtration. So biologists had studied this quite a bit, but not engineers. And so there were some challenges. For example, if we dry the xylem or dry the wood, then it just gets blocked, which means that it has a very short shelf life because it has to be kept wet and wood is degradable. And this happens because this membrane actually acts as a valve and seals against those dome-like structures that I just showed. We also need to achieve practically usable flow rates, which were too low in our initial experiments, and we don't know how it works with real water samples. And so over several years, we addressed this systematically. So we developed a simple process to store filters in a dry format, which now have long shelf life, more than 2 years, and it's very lightweight and easy to transport. We also discovered some interesting behavior. One of them was that the filters naturally block after filtering some amount of water. And so on one hand, it's useful because it can signal to the user to change the filter because the water flow stops. And that happens in a way that can be controlled by soaking in hot water. And so the filter can block before wood starts degrading. But it also means that these filters need to be replaceable. It's not a filter that you can just put in and then it works for months. It will have to be daily or weekly replacement. And we did a lot of characterization and modeling that helped us to understand how the flow rate scale with area and pressure and so on, which enabled us to design filtration devices based on this. So I don't have time to go into detail, but I'm just showing a snapshot of how we preserve the filters. So if we soak the filters in water and dry them, what happens is that these membranes get stuck against these holes in the dome and the flow stops. Or sometimes they get damaged. But if we soak in ethanol or other solvents and then we dry them, we can see that they are nicely suspended. And then when we re-wet it, water can flow through. And so we are able to get a good flow rate recovery compared to the fresh samples before drying. After soaking in ethanol, but in water, we get almost no flow rate, and it has this very strong length dependence, which we are able to explain based on percolation-based modeling. So this is just one example of how mechanisms at the microscale control the behavior of this material as a water filter. So this is a filter we made from a ginkgo tree, and it's 4 centimeters in diameter, and it can provide a flow rate of about 3 liters per hour with general test water prepared as per WHO specification. And you can see that the flow rate drops slowly over time, and it can produce around 50 liters of water at flow rates over 3 liters per hour, which is quite usable. And it can reject very nicely 1 micron particles. We also did field work in India, where in Himalayan region, in Uttarakhand, there is a lot of dispersed villages with many spring water sources, and microbial contamination is an issue, and conifers are locally available. So this xylem needs to come from conifers to make the filters. And so my students set up these filter systems to test, and we are able to filter about 25-30 liters of water at flow rates of 1 to 2 liters per hour. And these filters, when tested by third-party labs, the water that was passed through did not have bacteria versus the input water had bacteria. And with our collaborator, Amy Smith, and colleagues at MIT D-Lab, we also engaged people in trying to understand what are the attributes of filtration devices that people find easy to use and are attracted to. And so based on that, we developed this kind of a filter design where you have a container for water, a filter holder where you can easily replace a filter, and a container for clean water. And we also try to understand different user perspectives. So encouragingly, what we found is that there was high acceptance of xylem as a natural water filter, because people like the fact that it's a common material which is found in nature, and it's chemical free. And also low-income household preferred pay-as-you-go filters. So basically paying every week or daily as opposed to once every few months that's required for most of the filter cartridges today. But we also found that affordability was not the problem there, but it was more of an issue of awareness. And so we moved from the hilly areas to urban slums, where we found much more of a need and also a spectrum of people. But clearly there were some people who were aware of the problem, were seeking better solutions, and could not afford the current solutions, which is primarily cans of water that are supplied door to door, or people have to go and pick up. So these range from 5 rupees to 20 rupees for 20 liters, and there's often additional delivery charges, so you have to go to a different place and carry 20 kg of water. And so there is a potential advantage for xylem filters because it would avoid carrying of water, and we expect that the filters would cost about 8 to 10 rupees and provide more water than the RO cans. And even in the RO cans, the quality of water is still questionable. It's not always the same depending on the supplier. And so this is my student, Pratika, who did all of this development work, demonstrating a filter unit where we put in the water and we can get clean water that's free of the turbidity outside. And we are trying to assess the reception of potential users to filters like this. So very interestingly, we found that this natural appeal has a lot of interest from students. So this is a high school student who actually won an Intel prize. She was the first one in our lab to start working on this xylem filters. And another student, Pratika, she is basically demonstrating how to make xylem water filters and test filtration using turmeric at a science museum in India. And so we see a lot of potential in designing experiments that will engage school students to explore water and sanitation and hygiene issues and raise awareness about water filters. And so we are working towards developing material that could be used by students to design their own science experiments using xylem filter. So there is potential to improve access to safe drinking water using this technology by using local manufacture or easy procurement or shipping with low upfront costs, increasing awareness, engaging people in this process of supply chain or manufacturing, and also in disasters or emergencies. So for example, you could have a very lightweight filter that's a pouch that maybe costs less than $50, which you can store for a very long period of time and use it in emergencies to produce 20, 30 liters of water. We could also have household filters and then use these in a lot of other applications where microfilters are used. And this is an interesting cost comparison where this is the estimated range of cost per liter water, which is comparable to many of the solutions in the market in India, but the recurring cost is much lower. And that turns out to be a major barrier that we have come across in our field work. And so it turns out that for shampoos, let's say in rural India, these small sachets, which cost much less than the bottle, are the main thing that sells. And the upfront cost associated with larger quantities is a barrier. And can we do the same with drinking water, where we can have much more lower upfront costs and have a better financial model, plus social acceptance because of the naturalness of the wood that makes these filters more accessible, acceptable, and affordable for people in rural communities and other disadvantaged communities. So in the last few minutes, I'm going to go one level further in scale and talk about a systems level solution to water quality. And this relates to measuring trace contaminants in water. So we know that trace contaminants are a major concern, and we have seen quite a bit of this in the news. And there's a lot of different trace contaminants, arsenic, cadmium, chromium, and so on, which can have adverse health effects at very low concentrations in water when it's taken up over a regular basis. And if we want to have clean water, we need to be able to measure it. So we have to monitor water quality. And that water quality monitoring can advise on appropriate use or intervention. That could be policy or so on. For example, this is a groundwater well, which has been marked with a cross, which shows that this well is contaminated, so people should not drink water from this well. In this specific case, it's an arsenic-containing well. And so maybe it directs which sources to use for what purposes. Like maybe it's okay for washing utensils, but not for drinking. And then it also helps to identify and manage pollution sources. But the scale of the problem is staggering. So for example, in India, and a lot of this work is in India because of the networks we have and also some of funding sources tied to India. There is 14 million water sources. And so you can imagine the challenge of actually monitoring and advising on all of these. So it's a huge challenge. And how are these sources tested? So there's two paradigms. You take the water to a lab where testing can be done, or you take a field test kit and test it, bring it to the water sample. So here, there's often issues of limited sensitivity, fidelity, and management of supply chains. And labs have high sensitivity and fidelity, but transportation can be an issue. And transportation often is a significant part of the cost. So what we did was to try to understand how water quality monitoring works and what are the gaps that we can address. So this is my student Emily, who led this project, and it was in collaboration with Chintan Vaishnav and others. And so we looked at different water quality labs and what the framework was. And what we found is that the infrastructure is unable to test many of these trace pollutants of concern, because there's challenges like limited instrumentation at local labs, field test kits being inaccurate or not available, or difficulty in sending samples to central labs. And so we identified an opportunity to preserve and forward biochemical information from local labs or source to the state lab, which has adequate facilities. And because in the local labs, we don't have as much of analytical capability. So this is the picture that emerged. So you have the water sample, there's a local lab and a central lab. Central lab has good facilities and can measure trace contaminants. Local lab has limited capacity, but it can access the water samples. And so these pathways are blocked. And so we drew inspiration from this technique of blood spotting, where if you have blood, let's say from a neonate, on a card, you can save it and then analyze it later. So can we do the same with water? So if we can just mail the information or the chemical content of water, then it would resolve a lot of these challenges because it would avoid the transportation of bulky volumes of water. In some cases, they need to be acidified and are hazardous to transport. And this maybe also opens up the possibility of giving access to individuals to knowledge of the water quality that they are receiving. So there's several advantages if we can do this dry preservation of the chemical information of water. So maybe it will make it possible to cost effectively monitor these contaminants and lead to improved water quality management, regulation, and data collection. And it can also be very cost effective by making good use of high throughput instruments that are not locally available. So we looked at different kinds of materials that could enable chemical information to be absorbed, and preferably commercially available materials. And we also synthesized some zero gels for arsenic, which I won't talk about. but we are able to just take off-the-shelf materials that are used for water purification and show that they can be repurposed for quantitative adsorption and recovery of these trace contaminants. So here we can adsorb copper, nickel, and lead from water and release it and then measure it. And we can basically recover most of the chemical contamination and the information. So we developed devices, and this is one such device where you can, this device is in a pouch here. You can take it out, stir it in a water sample, put it back in a bag, and then it can be stored for a long period of time. And you can then take it out at a central lab. It can be shipped easily. And then when you put it back in acidified water, it basically produces a sample that's ready to go into the instrument. And so we are able to adsorb these samples in a very short period of time. And then after recovering the sample and measuring it, we can basically get fairly good quantitative measurements from different waters, including river water around the Boston area. So this is a totally end-to-end compatible device which can be used to measure heavy metal, and it samples them, stores it. It can be stored, transported very easily, and then it can be measured where you have high throughput instruments available. So just in summary here, we identified a gap in trace contaminant analysis through fieldwork in India, and then explored an alternative paradigm where we repurpose material for quantitatively adsorbing and preserving and recovering chemical contaminants that enable easy transport of chemical information. And so this has the potential to enable water quality monitoring of trace contaminants from a variety of situations. So I will stop here and acknowledge all the many people who have contributed to the work that I showed here. The many collaborators, different people who helped us, including many NGOs, MIT facilities, and all the funding sources. And thank you all for your attention.
Thank you very much, Prof. Rohit Karnik, for your wonderful talk and findings. Very informative, interesting talk, and high impact to the society, I can see. And definitely, I can see how Kritika and Emily did some experiments in India. And also, we can see the research is meant to solve the quality of water for better living, as to address our Sustainable Development Goals, SDG number 6, clean energy and sanitation. So I'm sure there's a lot of new discoveries that we can share here. And then I think the data, some of the data have showed some probably looks new to some of the audience. So now I would like to open for question and answer session. All right. Okay, so we have one question, Prof, from our audience. I believe this is in FB Live from Dr. Satyabama. So what's the biggest size of CNT membrane that you have fabricated so far and your future plan for the size?
So thank you. So we have made membranes that are up to a few centimeters in size. So I think our biggest one was maybe about 4-5 centimeters or so. Most of our membranes have been around 1 centimeter because that's suitable for measurements. And going forward, I think the kind of methods that I talked about that are scalable and roll-to-roll, those are the methods that need to be used and developed for membrane fabrication. So in thinking about these membranes, the fabrication process is actually simpler than CNT membranes because you can do everything in a roll-to-roll fashion, and it's and many of the processes were developed much faster than carbon nanotubes because they are easier in a sense for graphene. And so definitely these processes for roll-based or high throughput fabrication are the way to go for scaling up. So currently there's still a lot that we don't understand in terms of the basic flow properties and also different engineering approaches. And so I think the immediate future would be more focused on understanding those as opposed to scale up. We are also exploring applications in the chemical industry, trying to understand how different solvents, for example, go through And we have shown that the membranes can actually be put in a variety of different solvents and still retain their functionality very well and don't swell or have other issues. And so there are a lot of these aspects that we are studying and exploring. And once we are, as we build this fundamental base of both basic knowledge as well as engineering knowledge, that will be the foundation on which we can scale up these membranes. But in principle, we can envision a variety of totally scalable processes through which we can make these membranes at scale and cost.
Great, thank you, Prof. Such an intensive answer, I guess. Yeah, okay, any more question for Prof. Rohit? Okay, from Umi Kasum Abidin. Thank you, Prof, for your interesting sharing. Can a lab-on-chip device be designed for water analysis in remote area? What are the challenges?
Yeah, thank you. There is two approaches, I think, to this. So the approach that we took for water quality was how can we facilitate in a fairly simple and robust way this gap where we have these high throughput, high quality instruments, which if used properly would be very cost effective and give information on many contaminants. But they can't be used that effectively because transporting water is a problem. And so that's the problem that we answered. But of course, one of the limitations of that is you don't get an immediate answer. So the lab on a chip kind of approaches are actually better in a sense from the end goal, because the user could be able to get the answer right away. And there's several approaches that are being explored. The part of the challenge is that many of these rely either on creating special affinity-based materials, be it electrodes or materials that can be coated on surfaces that bind certain species, or they rely on specific chemistries. And so if you look at mass spec, the same mass spec instrument can measure all the elements. But if you look at chemistries or other surface affinity or other approaches, you need kind of different materials and different approaches for each species. And so that becomes an inherent challenge. So that is one of the challenges in developing lab-on-a-chip devices. So many people are actually working on it, and there's great progress being made. But inherently, it's a bigger challenge than trying to preserve the chemical information of contaminants in water in a dry format and send it. So that's a simpler approach in a sense. The lab-on-a-chip is a harder challenge, and many people are working on it. If we are able to, let's say, miniaturize mass spec to the extent that it will provide similar fidelity at low cost, then that would be an ideal thing. But till that happens, these other approaches, as they keep developing, in the future, we might have multiplex devices that are simple and robust enough. And a lot of the developments in lab-on-a-chip are being driven by the health industry, and there is quite a bit of advances and compact devices that are reasonably low cost have been developed, but they are still in the several dollars per use range. And so that knowledge from the healthcare industry or for healthcare applications can be translated to water. And the number of researchers in the area of water in lab-on-a-chip is much smaller than lab-on-a-chip for bio application. So I think there is actually an opportunity there where the learnings on lab-on-a-chip that are developed in the bio context can be applied to water. And there is quite a bit of room for improvement and advancement that will ultimately produce a more satisfactory solution than sending a sample.
All right. So time is our constraint right now, I can see. So if we can have a more time, I think I believe we can answer all the questions, but maybe the audience can write some questions from the FB Live so that we can answer the question later on, yeah? All right, so thank you very much, Prof. Rohit Karnik, and all the audience for an active participation and interaction. And last but not least, I would like to invite the Dean of Faculty Engineering, UTM, Professor Dr. IR, Dr. Muhammad Farid Rafiq bin Dato Abdul Kadir, to say a few words to the speaker and to the audience, and finally to close our distinguished lecture series. Over to you, Dr. Rafiq.
Thank you, Dr. Zeta. Thank you so much for sharing the session, and thank you for introducing Rohit Karnik to me, and to Professor Rohit Karnik all the way from Boston, USA. Thank you so much for accepting our invitation to participate in our UTM Engineering Distinguished Lecture Series. It is certainly an interesting topic, and water membrane, it is actually a very intensive research that we have here in UTM. We even have one center called Advanced Membrane Technology Center, and we also have another institute related to water. So water membrane is at the core and the forefront of our research here in UTM. Certainly interesting to have your talk related to these two important topics. Again, thank you so much, Professor Rohit Karnik, and to all of the viewers all around the globe, thank you for watching UTM Engineering Distinguished Lecture Series. Do stay tuned. We have many more lectures in the future, so stay tuned. Until then, bye for now. Bye-bye.